Hello, in this video we'll be talking about AP Chemistry's topic 1.6, Photoelectron Spectroscopy. Spectroscopy is an analytical technique to understand how much energy electrons have and their placement within an atom. It is great confirmation that the idea that electrons are in specific orbitals in atoms is actually valid. So let's look at what photoelectron spectroscopy is. First, let's look at a photoelectron spectrometer. You can notice this is a large piece of very expensive equipment, and again, it simply allows us to calculate how much energy electrons have within an atomic structure. So what does a PES, photoelectron spectrometer, do? So in photoelectron spectroscopy, energy, either ultraviolet or X-rays, is used to eject electrons from an atom. It only puts one type of radiation into the atom. So one type of energy photon bombards atoms. The electrons are in different energy levels, so they require different amounts of energy to eject. And when a photon hits an electron, if you'll notice here, when a photon of a certain energy hits an atom, it ejects an electron off of that atom, making an ion. If the total energy was 25 megajoules per mole hitting the atoms, and the electrons are measured to have a kinetic energy of 13 megajoules per mole, then how much energy did it take to remove that electron from the atom? Well, we simply subtract 25 minus 13, 12, and that is how much energy was holding that electron onto the atom. So that's how photoelectron spectrometers work, in that you just bombard atoms with a certain amount of energy, calculate the kinetic energy the electrons have after they've been hit, and the difference is how much energy they had when they were bound to the atom. Kind of cool. So when we read a photoelectron spectroscopy graph, there are y-axis labels and x-axis labels, of course. The y-axis label simply tells us the intensity, the relative number of electrons that were ejected with that amount of energy. The x-axis tells us how much energy was required, and it's usually logarithmic and backwards. So most energy is over here on the left-hand side, and the least energy to eject the electrons is on the right-hand side. So what that means is, on the left-hand side of the x-axis, it takes a lot of energy to remove electrons. So these would be the ones closest to the nucleus, because it's going to take more energy to remove electrons near the nucleus. And on the right-hand side, it takes just a little bit of energy to remove these electrons. These are our valence electrons because they're the farthest away from the nucleus and they have the most shielding. And then the height of the peak on this graph tells us the relative number of electrons on that energy level. So let's take a look at what these graphs look like. So these are just some examples of the graphs, but I want to show you a specific one that's very simple: hydrogen. So here's a hydrogen atom. And we all know that hydrogen has one electron in it. And so you'll notice the peak is at 1 here because there's only one electron. And the energy to remove that one electron from an atom is 1.31 megajoules per mole. So it takes a certain amount of energy to remove electrons from an atom. In this particular case, the PES tells us that's 1.31 megajoules per mole. Now let's look at helium. How many electrons does helium have? Well, it has 2, so we would expect the peak to be twice as high because there are 2 electrons in the 1s orbital. And we would also expect it to require more energy because helium atoms have 2 protons holding those electrons on. And so if we look at the PES for helium, you'll notice it took more energy, the peak shifted left, and there's 2 of them. And they each took 2.37 megajoules per mole to remove the electrons. Again, this is the amount of energy each electron requires to remove. Since they're both in the same energy level and the charge on the nucleus is the same, they take the same amount of energy to remove. Now, what would you expect to see for lithium with 3 electrons? Well, remember, lithium has a 1s orbital and a 2s orbital, and the 2s orbital is farther away from the nucleus. So here it is. The farther away electron takes less energy to remove, and there's only one of them. in that 2s orbital. In the 2s orbital, 1s orbital, there were 2 electrons, so twice as many electrons, but now the nucleus has more charge, and so it took more energy than the helium atom to remove each electron. Here's helium, 2.37 megajoules per mole to remove electrons, and here's lithium, another proton, harder to remove the electrons. And so now if we go to our next element, beryllium, notice that it takes more energy to remove the 1s orbital electrons, and now we have 2 electrons in the 2s orbital. So after beryllium, we go to boron, and boron, we have to go up to the 2p orbital. So where would you expect a 2p orbital to be? Well, it's going to be farther away from the nucleus, and so we would expect it to be somewhere over here. There's going to be more charge in the nucleus for boron, so all these peaks are going to shift to the left because they're going to be held more tightly onto the atom, so it's going to take more energy to remove them. And how will the height of the peak compare? Well, there's only going to be 1 electron in the 2p orbital, so we would expect it to only go up one unit here. And there it is. So this is the 1s orbital, closest to the nucleus, most energy to remove, 2s orbital, and the 2p orbital. So what is it going to look like for our next element, carbon? Notice that we have 2 electrons in the 2p orbital, and so now we have twice the height of the peak, and all the electrons are held on a little tighter because carbon has a higher effective charge. And if we keep going through these, we'll see the peak getting taller and the amount of energy to remove electrons getting higher and higher. So after neon, where do you expect our next element to be? Where do you expect it to be? We're going to sodium. Sodium's in the alkali metals. We're going to go to a whole new energy level and a whole new s orbital. So we would expect it to be down here somewhere and only 1 electron in that orbital. And notice it is. There it is. So PES is a way to figure out where electrons are in an atom, the electron configuration of the atom, and how much energy it takes to remove those electrons. Now, I'm going to go ahead and just go through these really fast. You're welcome to pause and look at them individually if you want. But I want to show you an atom, and I want you to figure out what element this is. So there's just 1 peak, so that means there's only 1 orbital. Notice that it goes up 2 units, so that means there's 2 electrons. So what element is this? Well, if you said helium, you would be right. What about this one? So we've got a whole bunch of peaks, meaning we've got 1, 2, 3, 4, 5 different types of orbitals. This is the 1s, this is the 2s, 2p, and notice the 2p is 3 times bigger than the 2s because 3 times as many electrons can fit in p orbitals. So 2p, 2s, 2p, 3s, 3p. So we know s orbitals hold 2 electrons, so this line here must represent 2 electrons. So 1s2, 2s2, 2p, 2, 4, 6, 3s2, 3p, 2, 3, 3p3. So what element would that be? I'm not going to tell you. I want you to figure it out on your own. So good luck. I wish you the best as you study PES. If you have any questions, please let me know.